everyone, and welcome to Saratoga County Sewer District number 1. We are going to do a virtual tour with you guys today, led by Dan Rourke, who is the Executive Director and has been for the past 5 years. He's going to give you guys an overview of what the sewer district does, and then we're going to follow the path of the water through the actual plant.
First off, we don't only treat residential wastewater, right? Wastewater from residential houses or commercial buildings. We also treat industrial waste. So some of the big industries that discharge here, the Stewart's manufacturing plant, which makes, milk, ice cream. That I'm sure everybody's been to a Stewart's or seen a Stewart's, right? I know I have. I love their coffee. But they discharge what's called a lot of BOD. Biological oxygen demand, okay? That's how you measure kind of how nasty the wastewater is, right? I'm sure you guys are learning about that. But basically, you want to remove that BOD so that you're not discharging into the river and stealing oxygen from all the other organisms that are in the river, right? So that's the goal. Another industry that discharges to us is Global Foundries. They're a semiconductor plant. They make chips that are in your phones, in your computers. They discharge about 3.5 million gallons a day, so they're a large user. Their main constituent that they discharge that we have to deal with is actually ammonia, right? So the ammonia comes in, we have an ammonia permit limit so that the Hudson doesn't get a large amount of ammonia, which is actually toxic. So we take in their ammonia, we treat it. That treatment process for ammonia typically happens in our activated sludge basin. So we'll talk about that when we get there. Some other constituents that are within the wastewater when they come to our facility is, I had mentioned BOD, total suspended solids, TSS we call it. TSS consists of a lot of different things, right? It consists of everything you wash off yourself when you're in the shower, everything you wash off your food, everything that goes down your sink, and yes, everything that goes down the toilet, obviously. But it's not just that, right? It's a whole bunch of other things. Fats, oil, grease, ammonia, as I mentioned. Heavy metals, right? We get copper down the line. We get zinc down the line. Anything that you put into your bodies does end up coming down the line. So yeah, there's a lot of different things that we end up doing. Let's get started on our screen and drip building. Basically, all of the flow, if you want to come over here, all of the flow comes through this gut well. Now it's really dark, you're probably not going to be able to see anything, but it's about 25 feet deep, right? So we're pretty far into the earth to be able to make gravity work to get the flow here from the entirety of the county. So that flow ends up coming through these 3 channels, and they hit these. These are our mechanically clean bar streams, okay? Basically, this is a physical removal process. They move really slow. This one's actually operating here, and they remove your plastics, your rags, anything that's going to damage the system downstream. Now, it removes all sorts of stuff, right? We've gotten action figures, we've gotten 2x4s, we've gotten money, right? Goes to the Christmas party fund. And then we've also, I think the craziest thing we've seen is a bowling ball come up through here. So very, very interesting stuff. But these are very robust machines. And they're not cheap, right? They're pretty expensive. So yeah, they protect everything downstream. After this, we end up going to what's called a washer compactor, and we'll walk around this side and I'll show you. So this is a washer compactor. Basically, you're taking out all the physical stuff, right? That physical stuff actually has BOD attached to it. It's got food attached to it that the organisms need in a process we'll talk about further. So you want to wash that food back into the system to maintain a balance in your activated sludge basins, okay? So it washes it, cleans it up, and it also makes it so it's tolerable as you bring it to the landfill. So you wash it, you compact it with these augers here, And as we walk further down, you'll kind of see the end product. It looks like a big garbage sausage. So, here's the end of the chutes. If you look down this chute right here, it falls onto the conveyor that you're seeing now and ends up going to the landfill. If you could peek inside here, that's what I'm talking about with the garbage sausage. It ends up coming out, dumping on here. Now, this conveyor also takes grit, right? So you don't want your inorganics to make it any further. The screens are only 3/8 of an inch. So anything smaller than that, sand, small stones, corn, right, makes it through the screens into our grit system. And we'll take a peek outside at the grit channels. But those channels end up bringing it back to here, to over here are grit classifiers. And those classifiers drop the water out, just like a centrifuge, right? Drop the water out, feed the solids up, and then dump those solids onto this belt, which we'll see as we walk a little bit further down. So this one's operational. You can see some of the grit falling out. Again, you get all sorts of stuff. Little plastic, sand, small rocks, small stones, pieces of corn. And this classifier ends up taking that out of the system, again, to protect the downstream elements. Here is our dumpster that ends up making it to just a typical landfill. There's no special disposal required for this. It just goes to a typical landfill. So we just got through building 4 here. That's our screen and grit building. I had mentioned the grit classification system. You saw the mechanical portion of that. The physical portion of that are these channels. Now, we just got snow last night, right? So it's a little more difficult to see. But those channels you see with the railing and the vent pipes on the end, just past that black corrugated pipe. Basically, the goal of those is to slow down the water coming in to about 1 foot per second, 0.8 feet per second. What that does is it allows the grit and those heavier materials that I have mentioned inside fall out, but it keeps the organics suspended, right? So it's all about specific density as you move the water forward. So from there, from those grit classification tanks, they end up going to this building. This is our main influent pump building. I'm going to talk about it a little bit out here just because it's a little noisy. So we have 5 200 horsepower pumps down in the basement. They can sling about 11,000 gallons a minute each. So when you design a facility, you need to take out the largest unit and still be able to handle flow with the remaining units. So here, 4 pumps can move about 60 plus million gallons a day. So this plant can hydraulically handle over 60 million gallons a day. There's centrifugal pumps, right? There's different kinds of style pumps. These are centrifugal pumps that use different pressure centers, right, to move that water. And also in this building, we have our NPW system, which is our non-potable water system. So we take a benefit on the back end of the plant, right? So the treated water, we actually put back into our system to use for certain aspects of the facility. Whether it's washing tanks, washing our gravity belt thickener, which we'll get to, or washing our belt filter press, which we'll get to. We save a fair amount of money by reusing the water that we have cleaned for certain operations in the facility. So we'll take a walk inside just to take a peek at these pumps. And so you can see what I'm talking about. So, welcome inside. It's a little loud in here. So I had mentioned the main sewage pumps that move those 11,000 gallons a minute per pump. Those are in the basement. Those are downstairs. You can see them. We typically operate 2 pumps. In a high flow situation, we'll do 3 pumps. We only have about 15 minutes. If this station goes down, we have about 15 minutes until we're overflowing the last building here. So this is very important. If we have a power outage, you'll see our operators running like chickens with their head cut off to try to get this thing up and running within those 15 minutes, which they do pretty regularly. So kudos to our operators for the effort they put in.
So, we just came from our main influent pump building, which is way on the other end of the site. We walked up our road. Both of these roads, this one and the one on the other side, have the force mains that carry that flow that we were talking about, that those pumps move, up to our primary clarifier. So I'm standing on our primary clarification system. This is our old side of the plant. Another little bit of history is this was built in 1977. The other side of the facility, which you'll see a little bit later, was built in 2010, mainly to handle the increase from global foundries. So, primary clarifiers. Just like the goal of the grid system, the goal of a primary clarifier is to use gravity to its advantage, right? It slows the velocity of the water down, and it drops the larger organic material out. You typically remove about 30 to 40% of your biological oxygen and your BOD in your primary clarifier. So these are about 12 feet deep here. They run on what's called a chain and flight system. They run really, really slow because they don't want to stir up all the sludge that's settled to the bottom. It pushes that sludge to the front of the tank, and then down in this basement here, there are primary sludge pumps, right? So where the camera's panning now, that goes down about 20 feet to some primary sludge pumps. Those pumps take that sludge and pump it to a tank that we'll visit later for future processing. This tank also helps remove floatables, right? And grease that comes out of suspension and floats to the top of the tank. So not only does it settle sludge out, it allows things to rise, and that's how we end up removing grease out of our system. That comes from a whole load of places, right? I mean, if you've ever eaten at, I don't know, Cracker Barrel or any restaurant, you see what's left on the plate, and that comes to us. All that grease comes to us. Or maybe you guys cook at home and you got a pan full of grease and you just dump it down the drain. I implore you to not do that. It makes our lives miserable. Put it in the garbage. It's the better route. Or put it in a jar and put it in the fridge and let it solidify, right? Because what happens is these end up having enough grease on top where it looks like you can walk across them. And it costs money to get rid of it, right? And it causes headaches in terms of maintenance. So that's the basis of the primary clarifier. Let gravity do its job and reduce the load to the activated sludge basins, which we're going to visit next. All right, so after the primary clarifiers where we were just at, the flow ends up coming into our activated sludge basins, right? This is where a lot of the biological, or I should say all of the biological activity happens, right? The load from the primary clarifiers, the BOD, the TSS that I had mentioned before, the ammonia, it comes into this tank, and there's all sorts of different microorganisms that end up using that as food to reproduce. Heterotrophs, autotrophs, they end up using that to reproduce, as I said. So these tanks are about 1 million gallons apiece. They go down about 18 feet. One thing that the bugs really need in order to survive is not only food, but they need oxygen, right? So if you can see on the top of these tanks, you kind of see the wavy motion and really, really fine bubbles that are coming up from the bottom. We have about 9,000 diffusers in these tanks on this side alone. We have another 11,000 on the old side. They provide really small bubbles. So the smaller the bubble, the easier it is to diffuse in water. Also, the colder the water, the easier it is to diffuse air and water, right? So we end up getting what's called dissolved oxygen readings. And that's how we know how much air to provide to the system. You typically want to maintain a DO above 1, closer to 2. Sometimes when you're dealing with different pollutants, such as ammonia, you want to maintain 3 or above. So maintaining that is a large strain on the electrical grid and our electrical bill as well. A typical wastewater treatment plant spends about 67% of their electrical budget on this process right here. Because if you think about it, those blowers are pushing against all that pressure of the water that's sitting on top. So 18 feet of water, is about, 7.5 PSI, something like that. And it's 24/7. So not only does it remove BOD, TSS, and ammonia, but it also, in order to do that, right, you actually need to return mass from what we're going to visit next, which is the secondary clarifier. So you need to return those bugs back to these tanks to actually eat the food that's coming from the primary clarifiers, which we were just at. And what you do is you try to maintain a couple different operational parameters. One is called food to mass, right? So the food that's coming off your primary clarifiers compared to the mass that's in your system. And there's certain ratios that you want to try to maintain. The second operational parameter is called either SRT or MCRT, right? Sludge retention time, solids retention time, or mean cell residence time. Basically, how long does one cell stay in the system? We typically operate somewhere between 5 and 12 days with typical constituents like we have DOD, TSS, and ammonia. That's good. Industrial facilities that deal with a lot nastier stuff sometimes have MCRTs 15 or 20 days, 30 days. They keep it longer so it can grow more robust and acclimate to the environment. That's pretty much it here for the activated sludge basins. It's where the magic happens, I like to say.
So we just left the activated sludge basins. I had mentioned the air that was required, right, for those bugs, for that microbiology to do what they need to do. We're just going to take a quick jog into our blower room. I'll show you the blower that actually does that work. It's a 700 horsepower motor, right? So it's a lot of electricity, and it can move up. Each one of these blowers can move upwards of about 13,000 cubic feet per minute. Again, against that pressure I had mentioned of about 7.5 psi. So I'll mention again, high electricity load, high demand, and as we walk through, you'll also see our emergency generator. I haven't mentioned this yet. We're required to have emergency power here at the plant because guess what? Nobody stops showering, nobody stops going to the bathroom when there's a power outage, right? So we still need to maintain our efforts in our cleaning of wastewater to get discharged to the Hudson. So you'll see this big cat generator. I believe it's 1.5 megawatt. So we'll take a walk through right now. So here's the generator, all the size of a freight car. Yeah, pretty self-explanatory. Runs on diesel. It's going to get very loud.
All right, so after the activated sludge basin and the blower room, the wastewater then goes over the weirs, which you also saw earlier, that really turbulent flow, that we can pick which secondary clarifiers we want to come to. This here is one of our 8 secondary clarifiers. The goal of these is to settle the solids that are being used in the activated sludge system down to the bottom. Right, so again, similar to the primary clarifiers, letting gravity do its thing. So the sludge on the bottom of these have 2 things, right? They do 2 things. One, it's returned to the aeration basins, as I had said previously, to be the mass of the system, to eat the food that's coming off the primary clarifiers. Second, it gets wasted, right? So it's not a full cyclical process where we can just use what we have and not get rid of any, right? Just like any population curve, right? It ends up being exponential and you need to get rid of some. So, we're going to go look at what happens when we waste from the bottom of these secondary clarifiers. The other aspect of these secondary clarifiers is, as you can see, the top of it has some scum on it for some process changes that we're going through, seasonal changes, water temperature changes. So the arm on top that you see ends up scraping that scum into a drain and goes back to the head of the plant to get treated again. So it's not getting discharged over the weir. So from here, right, we take the wastewater and we go to our final process, which we'll go to next, which is UV disinfection. And one other thing I did not mention here is it's hard to see with the snow, right? But there's a center well. That center well has all of our return activated sludge, RAS, that goes back as the mass in the system. And what's neat about these secondary clarifiers is that they act passively. So they act just on water differential, right? Just on the pressure to push that sludge into that center column. These things are only about 1.5 horsepower as compared to like the 700 horsepower blower that we just saw in the previous segment. So onto the UV system. All right, so final step of the process. After the secondary clarifiers, the wastewater, final effluent at this point, comes to the head of these tanks. The head of the tanks on the other end, and it ends up going through a disinfection process. There's a couple different ways to disinfect. The method that we have on site here is ultraviolet UV disinfection. So ultraviolet disinfection doesn't necessarily kill the bacteria, right? It ends up deactivating the DNA so that it can't reproduce after it leaves the facility. Another type of disinfection is using chlorine, right? The New York State Department of Environmental Conservation has been trying to get away from chemical disinfection and moving towards more UV disinfection so you don't have byproducts, going to the Hudson River. This is another big energy sink for us. Costs a lot of money to do this UV. We have 864, 150 watt light bulbs, I believe. So again, large energy sink. After the disinfection process, it hits these weirs, overflows these weirs, and ends up going to the Hudson River. One thing that I haven't mentioned throughout the process too much is the need to sample, right? We need to sample this wastewater to test it to know if we're meeting our permit. This sampling happens after these weirs. Actually, the sample box is right behind you. It's the white box. We do a 24-hour composite sample so that we get a decent idea of what we're sending to the Hudson River.
Given the fact you have a weir system in here, even though this is the final effluent where water has to reach a level and pours into there, that must mean there's some physical settling of some material still.
Yes.
Is that right?
Yes, absolutely. It's part of our maintenance program. So we will have sellable solids, we will have suspended solids hit these tanks. They will inevitably settle out, just as was stated before it goes over the weir. What's interesting for us is because we have such a high ammonia load in global foundries, the nitrification process goes NH3, right, goes from ammonia to nitrate to nitrite to nitrogen gas. But to get to nitrogen gas, you actually need an anaerobic environment. You need an environment where there's not much air. Perfect environment, these tanks, right? We're not pumping air into these tanks. The bottom of them is a very anaerobic environment. So you end up getting sludge popping to the surface with that nitrogen gas getting released. So we switch every couple of weeks to clean these tanks to ensure that that's not reaching these weirs and then reaching the Hudson River. All right, so after all the processes we just went through, now we have to deal with what's left over, right? So what's left over is what we poetically call sludge, right? So when we waste the sludge from the secondary clarifiers, which was mentioned before, they end up coming, that sludge comes to this room. This is the gravity belt thickener room. In order to make the gravity belt thickener work, it requires chemical. That chemical is in this tank that you're about to see. It's called polymer. This polymer ends up binding the molecules together to create a bigger particle and allow the water to drop out. And it also allows it to squeeze better in the belt filter process. So we'll go take a look at the gravity belt thickener in action. All right, so this is the gravity belt thickener. We'll get you a shot up top here, but just a quick explanation. On this side of the gravity belt, the waste activated sludge comes in at about 0.2 or 0.3% solids. It goes across this belt, again using gravity to our advantage to allow the water to drop out. As you can see, it's kind of dropping out the bottom here. And that thickens the sludge up. And again, this side is the thickest side. So we'll take you up here to have you take a look at it. The reasoning behind this is to decrease the needed sludge storage capacity, right? Get rid of some of the water, thicken it up, so that you don't have to fill massive tanks just to hold water. You fill them to hold the sludge. Okay, so after the sludge is thickened, and that primary sludge that we talked about back at the primary clarifiers, that gets pumped to our combined tanks, right? Out of those combined tanks, they end up coming to these. These are called belt filter presses. This is the head end of the belt filter press. We use that same chemical I was mentioning before, polymer, to do the same thing. Bind the molecules together, allow the water to drop out. This is the gravity section, just like you saw downstairs. This over here is the pressure section. So you have a hydraulic pressure, and you have these belts that you see wound through this whole thing, squeezing that water out of that sludge. Typically, we'll feed this piece of equipment at about 3 to 3.5% solid, and on the back end, it comes out at about 22 to 23% solid. Aptly named cake, right? Looks like dirt. I won't say it looks like cake because then you'll never eat cake again. But from there, it gets dumped into a truck. Currently, it's dumped into a truck and then hauled to another facility called Grasslands in Chattagay, New York, where they end up making compost out of it. All right, welcome to the beautiful rooftop here where you get one of the best views for the sewer district. Couple of things I wanted to show you up here. One, as you can see in the background here, we're installing a solar field. It costs about $1.3 million, I should say. It's going to save us about $70,000 to $80,000 a year in electricity. One of the green initiatives that we're trying to take advantage of. One of the sustainable things we're trying to take advantage of because that land is unusable. Right now it's just a landfill with our ash. So we thought that made good sense. The next sustainable idea that we're trying to implement here is using anaerobic digestion of our sludge, which will be coming off that belt press, to produce methane gas. So that process basically breaks down the sludge, produces methane gas, and you can use that methane gas for something green, right? Produce electricity, clean it up, pump it back into the natural gas line for heat or electricity generation. That project is ongoing. We're hoping that moves forward, but that's another one of our sustainable goals. All right, so a couple of things too to finish up with. The scale of our operation, right? So again, we serve about 150,000 people here. We treat about 15 million gallons a day. And this process is not cheap, right? It costs, our annual budget is about $25 million to be able to do this work. Sounds like a lot of money, right? So that money goes to operations and maintenance of the facility, but it also goes to capital projects. And not just here, but also in the collection system as well. We have 55 people that work for us currently. So it's a good size operation. We have a full staff lab, ELAP certified lab here. We have operating staff, maintenance staff, admin staff, management staff. So it's a heck of an operation. One thing I wanted to mention as well, two things actually I wanted to mention. One is an organization that I'm a part of called NYWEA, the New York Water Environment Association. So NYWEA, NYWEA. $5 to sign up as a student. You get information on the industry, what's going on. You get networking opportunities. It's a good thing to join up for somewhat cheap costs. Although $5 to me in college was a lot of money, so I get it. Second thing, in that organization, I'm part of a committee called the DE&I Committee, Diversity, Equity, and Inclusion. One thing that this industry is trying to combat is we are very, very stereotypically white and male. So we want to get diversity, we want to get inclusion of all sorts of people of different racial backgrounds, different socioeconomic backgrounds. The more diverse you are, the better you are at problem solving. At least that's my belief. So again, thank you. Best of luck to all. Please don't hesitate to reach